Hello.
Hello, nice to see you guys.
Good afternoon.
Good afternoon. Hello, everyone. So, last time we discussed in details this RC electric circuits, and so it's the end of our lecture, and we have shown that in RC electric circuits, it is possible to realize direct current, which is constant in direction, but with magnitude, which is time dependent. So we discussed how electric charge accumulated in the capacitor and electric current flowing through such circuit will change in time while electric capacitor is charging. So once it is charged and this electric charge accumulated on its plates reaches maximum magnitude, then electric current in the circuit stops because capacitor actually represents a open circuit because we have just some insulator between two conductors. So it cannot continue direct current to flow through it once the capacitor is charged. And this potential difference at the capacitor, once it's fully charged, will be equal to potential difference at the terminals of the battery, which is used in this electric RC electric circuit. So today we start a new topic that will be already we make a transition from electricity to magnetism. So we will introduce general features of magnetic field, describe how magnetic field interacts with mobile electric charges. So we'll talk about already not electric force, but magnetic force. And also we will highlight the differences between magnetic force and electric force. So there is a question about chapters for midterm. So you can always double check everything in the manual, which actually I encourage you to do time to time. So you follow the process and know where to find some additional information. But for this midterm, we will have, yeah, it's already mentioned 510. So it will be up to magnetism. So everything what we discussed until today. So this like magnetism is already not included into the scope of material, which will be covered by first midterm. So that's why please take your time and look, like recall all this material in order to be able to solve the problems. Okay, so let me switch then to our slides. So it was known since dawn of history, some magnetic features of certain materials, and most likely it was some iron, which nowadays known as ferromagnetic materials. So we will discuss this classification of materials in terms of their magnetic properties. But some iron needle on a leaf floating on water. If this needle is magnetized, and it starts to arrange in space in order to show the directions of geographical poles, actually magnetic poles of our planet Earth. And today we will also a bit discuss the origin of this magnetic field. So people were using these features of actually compass quite for a long time, and obviously this is plays an important role in our life in general on planet Earth, because without this magnetic field around planet Earth, it would be impossible to survive on our planet. So it protects us from solar wind, so-called, this flow of ionized particles, mostly protons, which travel from the sun, and they interact with magnetic field, which kind of serves as some shield, preventing too intense interaction of this solar wind with our upper layers of atmosphere of our planet, and otherwise it would be just blown away, and there would be no condition for a stable atmosphere on our planet. So it plays really a remarkable role in all life, not only human, but any form of life on our planet. So definitely there is some interaction between magnetic field and electricity in general, but actually that was shown not so long time ago. It was only in 1819 was shown that magnetic field can be created by electric current in a wire, and that was kind of direct proof that electricity has to do something with magnetic field, and they are related to each other. So initially it was just considered some permanent magnets, with was assumed that they possess some poles, like named as N and S, so stands for north and south poles. And if we have some permanent magnet have two poles, always any magnet possesses two poles, and it is considered that so magnetic field is represented, can be represented by magnetic field lines, and sign like B vector is used to represent magnetic field. So also it provides a direction of magnetic field in any point of space. So it is assumed that magnetic field lines originate at they kind of, well, it's, if we compare now electric charges and magnetic field poles, so we were claiming that in electric case of electric charges, electric field lines originate on positive charges and terminate on negative. So that is not applicable for magnetic field lines, because we assume that magnetic field lines, they are coming out from north pole. So we have something like this. These magnetic field lines, they are coming out from north pole of the magnet, and they go in the south pole of this magnet. And so we have something also like this. We also keep in mind that what is interesting, maybe I can share with you my screen 1 second now. Okay, so if we look at our planet with this magnetic field representation, we can see that the global, let's call it, magnet of planet Earth, its south pole is actually located close to North geographic pole, and its North pole is located close to the South geographic pole. So we have North magnetic pole next to South geographic pole, and in the contrary. Observing some deposit, like magnetic deposits of lava from ancient times, it was possible to prove that during the history of our planet, the direction of magnetic field, so orientation of magnetic poles of our planet was changing during the history. So it's not really a constant orientation. Moreover, we observe continuously moving of these locations of south and north poles with respect to geographic poles. So it changes year after year, not much, but it's constantly moving. So let us consider some general model which explains the existence of this magnetic field. So it's not that we have, as shown here in this image, some permanent magnet embedded in our planet. So according to nowadays understanding of the geology of planet Earth, we have very hot, quite like solid central core of our planet, which is surrounded by magma. So that is melted very high temperature, like a few thousand degrees of Celsius hot melted material, which is partially also ionized because of this extremely high temperature, and this convection between hot central core region and external Earth crust cold region. So we have heat transfer between this hot and cold internal and external regions. This convection, it's a motion of a lot of melted material, magma, inside the planet, and motion of some charges actually is the origin of magnetic field. So if we have this motion is quite slow, however, we have huge masses of this magma moving continuously inside the planet, and this motion creates, it works as some generator of current generator inside the planet, and this current associated with the convection of hot plasma between the central and external parts of the planet creates this magnetic field. Of course, there are some other contributions to the magnetic field of our planet. However, the dominant one, which defines the magnetic field of our planet as we have it, is associated with the convection processes of magma under in the internal part of our planet. So as you see, this magnetic field lines, they go quite far outside from the planet and from our atmosphere. So when we have some charged particles moving from the sun, they interact with these magnetic fields. They start to follow them, and kind of some of them within these pole regions, since they're collected from other parts and moved to the pole regions, we observe higher concentration of these particles, which ionize atmosphere, upper layers of atmosphere, and we see this aurora lights in northern and southern latitudes. So when we do have very when we are closely located to the geographic poles, we see this light in the upper layers of atmosphere because of bombardment of these charged particles, mostly protons, originated from the solar wind. If we don't have a magnetic field, such ionization would happen like everywhere, all over the planet, and would just cause blowing away the atmosphere from our planet. That would be definitely not possible to develop any life on our planet Earth. So now let us maybe switch back to our slides and so let us talk now about magnetic force, which was shown to exert some, to be exerted on mobile charged particles in magnetic field. So based on some experimental observations, this we denote magnetic force, also a vector quantity. It was found to be related, like proportional to the charge carried by mobile particle, and also it was proportional to the speed of this particle. However, that was not the only observation in terms of magnetic force. Also, it is important to highlight the dependence of magnetic force on the orientation between velocity vector of this charged particle and magnetic field vector. So if, for instance, we have magnetic field vector parallel to to velocity vector, magnetic force is equal to 0. So if there is some angle between magnetic field and velocity vector, so they are not parallel, then magnetic force vector is perpendicular to both magnetic field vector and velocity vector. So taking this into account, by the way, another factor which should be highlighted, that the orientation of magnetic field vector actually depends on the sign of the electric charge. So if we have, if we change sign of electric charge from positive to negative, then electric field vector will just be rearranged in the opposite direction. So summarizing all these features of magnetic field, it is possible to write the general equation which describes this magnetic field vector. So magnetic field vector is equal to electric charge times vector product of, so you have cross product of velocity vector and magnetic field vector. So that is equation which in vector form defines the magnetic field vector. So if we have, for instance, such a situation, let's say we have some positive charge with velocity vector v, then in the given moment of time and given point of space, we have magnetic field vector B, then magnetic force vector will be oriented perpendicularly to the plane in which these two vectors, velocity and magnetic field, are located. And also, if we have, let's say, two charges, one negative, one positive, then we have some magnetic field vector, and they move both upwards. So this is the orientation of velocity vector for positive and negative charges. Then we will have, it's all based from, comes from this vector product features for positive charge, the orientation of magnetic force vector will be to the right. Let's assume this direction to the right. And for negative to the left. So they have opposite directions. And that is one feature which I actually mentioned you about. If we change the sign of electric charge, then direction of magnetic field vector is rearranged in the opposite point. So it's pointed to the opposite direction. If we have equal by magnitude charges but different in sign, so we'll get equal by magnitude magnetic forces but oriented in different directions. So the magnitude of magnetic force can be then calculated according to the rules for vector product as absolute value of electric charge, magnitude of velocity vector means speed, magnitude of magnetic field, and sinus alpha, where alpha is the angle between velocity vector and magnetic field vector. So now it would be good to highlight some differences between magnetic and electric force. So we know that electric force is parallel to the electric field lines, and magnetic force is perpendicular. So we have shown that no matter what, magnetic field force, magnetic force is oriented perpendicularly to magnetic field lines. So we can write that electric force is parallel to electric field, and magnetic force is perpendicular to magnetic field lines. So another important feature is that electric force acts on any charges, means stationary or mobile. However, magnetic force acts only on mobile charges. So the magnetic field cannot act on stationary electric charges as electric field does. Electric force does work, so because it's oriented in the direction of displacement of electric charges, and since magnetic force is always perpendicular to the velocity vector, it only can change the trajectory of charges, but it cannot perform work because then we have right angle between force and displacement, so projection of a magnetic field force on the direction of displacement will be always equal to 0. So that's why this feature actually implemented in some equipment also, which deals with orientation of some flux of charged particles. For instance, in this old-fashioned electron gun TVs, we had for acceleration of electrons, in order to provide them certain speed, there was used electric field, and for orientation of this beam in order to scan the surface of the screen and cause this luminophore excitation and luminescence. Was used a set of different coils with controlled currents, so they control magnetic field, and by acting on moving electrons, it was possible with a high precision control position of this electron beam and define where it will hit the surface of the screen. So in like SI units for magnetic field is Tesla, and denoted as capital T. So 1 Tesla is defined as 1 Newton over ampere times meter. Now let us discuss motion of a charged particle in uniform magnetic field. So obviously, if we are dealing with magnetic force, we have to deal with mobile particles. So we discuss motion of charged particles in this case, uniform magnetic field. Before we start, we need to define how we graphically show the orientation of magnetic field. And for this purpose, it is convenient to use such rule. If we have a dot, so these dots represent the fact that we have magnetic field lines coming out from the plane where we draw this. And if we have crosses, we have magnetic field going in the plane, perpendicular to the plane, but um, in the plane where we draw them. So in taking this into account, we can now draw some situation of a mobile charge in uniform magnetic field. So let us, maybe I just clean this. Let us assume that we have some uniform magnetic field oriented perpendicularly to the plane and of this image, and these lines of magnetic field, they go in the plane. So we can consider some positive charge, which is moving with velocity vector v, and there will be some magnetic field force exerted on this charge. Since this force vector is perpendicular to velocity vector, when we have some equilibrium condition, this particle will move in a circle because magnetic force will just always push this particle to the center of this circular trajectory and will compensate the centrifugal force which this particle will experience while moving on a long circular path. So taking into account this, we can write expression for the magnitude of magnetic force. So in this case, it will be electric charge Q times speed times magnitude of magnetic field, because in this case, they are magnetic field vector B and velocity vectors. They are perpendicular to each other, so sinus alpha angle between them will be unity, so we can write like this. And also from other side, we have this centrifugal force, and that should be compensated under steady state condition when we have circular trajectory. That is equal to m mass of the charged particle times centripetal acceleration. And taking this into account, we can write that QBB is equal to mass of the particle times speed in the second power divided by r, radius. And this is a radius of the circular trajectory. So from this equation, we can express some unknown parameters. For instance, we know mass, magnetic field, and speed. So we can calculate the radius of this trajectory. That will be equal to m times v divided by qb. What is also very important when we deal with such motion of charged particle in uniform magnetic field, that's also the frequency or also period of one rotation around like about the center along this circular trajectory. So angular frequency omega can be defined as linear speed divided by radius. So that's from our previous course of mechanics. You should remember the relationship between angular and linear speed. So in this case, it will be equal to Q times B divided by M. So also for the period, we can write this period of one rotation will be 2 pi r divided by v, and will be actually 2 pi divided by omega, and that will be 2 pi times m, mass of the charged particle, divided by electric charge times magnetic field B. So this frequency, omega, is called cyclotron frequency, and that is quite commonly used technique to measure this cyclotron frequency for determining effective mass of electrons or holes, like other charge carriers, form of charge carriers in semiconductors, in some solid states, solid state materials, in particular, like metals or semiconductors. So if we place some material, solid state material with mobile charges inside uniform magnetic field, then these charges, mobile charges, they eventually will start moving along some circular trajectory because of the effect of magnetic field on them. And by measuring this cyclotron frequency, it is possible to calculate effective mass of charge carriers, because if you see, if you take a look here on this equation, for instance, we have magnetic field, mass of the charged particle, which in our case, if we deal with some solid state material, will be effective mass of electron, for instance, and their charge. So we know charge of electrons, we know magnetic field because we can measure it. So where we put this material, if we measure this cyclotron frequency, then we can easily determine effective mass. So in solid materials, effective mass of charge carriers is different from real effective mass of, for instance, electron in free space, because we have some periodic potentials of crystalline lattice, and that imposes some, let's say, effective medium where this charge is moving. So it behaves like it possesses a bit larger or a bit smaller mass in comparison to real mass in free space. So that changes from material to material, and in order to determine effective mass of electron in such solid states, this effect of circular motion of charges in uniform magnetic field is widely implemented. So now I would like to summarize. We introduce the concept of magnetic field, explain on the example of a permanent magnet that we have some north and south pole, and magnetic field lines are coming out from north pole and go in the south pole. So we also discuss some general model of magnetic field generation around planet Earth, which is related to conventional motion of hot magma inside our planet when we have convection heat transfer between hot core and cold external crust area of the planet. Also, we introduce magnetic force, which is always oriented perpendicularly to the plane of where both magnetic field vector and velocity vector of charged particle are oriented, and we discussed the motion of in this particular case positively charged particle in uniform magnetic field, deriving equations for the radius of the circular trajectory, cyclotron frequency, and period of one rotation along this circular trajectory. So if you have questions, you are welcome. I would like to remind that on Saturday we have first midterm, so please be aware of that. Please organize your internet access as safely as possible, so you have less chances for interruptions. Log into the system prior to exam, at least like 20 minutes prior to the exam, and prepare to do your best. When you see the problems, please read them all, define which problems are the easiest, solve them first, and then save all the rest of the time to think about problems which are more complicated, because that is, from my point of view, the best strategy to not to lose points, because if you stuck with first problem, which appeared to be the most difficult one, or some problems which similar problems you didn't solve before, so you may just spend all your time solving this problem, and then even so that you know how to solve other problems, you will not have time to do that. So I encourage you to finish with easy problems at the beginning, and then all the rest time do your best to solve other problems and get the maximum possible points for this midterm. And I wish you good luck with your first midterm. Have a good weekend and see you on Monday.
Thank you.
Thank you. Goodbye.
Bye-bye.
Okay. Bye-bye.
Have a nice day.
Bye.